the review. Where are we? Here we are. Oops, definitely not that. Well, on the top left is the original. So this is the original, right? This is the original. And there are also several other drawings and several other potential scaled copies, right? They're determining if any of the other copies are scaled copies. So if they are scaled copies, right? We know that the shape has to be the same. So for example, we can automatically, if that's the original, we can look at drawing 4 and say see ya, right? Because it doesn't look like an F, right? So the shape has to resemble the original. We can get rid of drawing 6. Notice that F here in the original, the top edge, top line here is longer than the middle one, right? It's the length of 2 units. This is 1. And if you look at drawing 6, they both have the same length. So we can say see ya to this guy as well. Let's take a look at the other ones. So I'm going to put some numbers down, and that's what you should do as well. This measures 2. This guy measures 1, and the height here is 1, 2, 3, 4. All right. So if it's a scale copy, the same scale factor was applied to all the lengths, right, at different distances. So let's take a look at this one. This is 1, 2, 3. This is 2 over here, and this is 1, 2, 3, 4, 5, 6. Well, I can tell you that. How do I get from 2 to 3? 2 multiplied times what is 3? It's 1.5. 4 times 1.5 is 6, but it's 1 times 1.5, 2. 1 times 1.5 is just 1.5. So this fails. So this was okay, and that guy failed. So we can erase all this. I can tell you that this guy is a no. So drawing 1, not a scale copy. Drawing 2, this is a 2, right? And this is 1, 2, 3, 4. Looks like everything is double. So if the height here is 8, we're in business. 1, 2, 3, 4, 5, 6, 7, 8. Good. Scale factor of 2. Look, 2 times 2 is 4. 1 times 2 is 2. 4 times 2 is 8. So drawing 2 is definitely a scale copy. Drawing 3. Okay, really? Anyways, we'll look at the height. 1, 2, 3, 4. So if it's a scale copy, right? So how did the 4 become 1 times 1, right? The scale copy should have been 1. So everything should have remained the same size. It should have been the 4. The top line should have been a 2. And this one, the middle line, should have been a 1. But if you look up here, that's a 4. And that's a 3. So there's no way, if you think about it, how did that 2 become a 4 times 2? How did that 4 become a 4 times 1? You can already tell the scale factors are different. So erase all that. Drawing 3 is out of contention. So far, only drawing 2. Let's take a look at drawing 5. This is 1, 2, 3. This guy here is 2, and this is 1, 2, 3, 4, 5, 6. So this is definitely a potential. So if you think at the scale factor, how can 2 times what is 3? What can I double to get 3? Well, times 1.5. 4 times what is 6? Times 1.5. And, oop, it fails here again. Oh, I made a mistake, so I'll go back to it. So 1 times 1.5 should be 1.5, and this one is 2. So this one fails. So drawing 5 fails, right? It was almost there, and in actuality, I made a mistake. So drawing 5 definitely fails, but drawing 2 actually doesn't fail. I just failed to see. So it's very similar to drawing 5. So if you look at the top, it's 1, 2, 3. So 4 times 1.5. So let me just make a letter here. Times 1.5 is 3. So that's good. 1, 2, 3, 4, 5, 6. This is 6. How did the 4 become a 6? Times 1.5. And this line right here is actually 1.5. I made a mistake. So how does 1 become 1.5? Times 1.5. So with all the dimensions here multiplied by 1.5, yes, they were. So drawing 1 is definitely a scale copy. So we're good here. Okay. Then we gotta look at the last one here. So we know that 1 and 2 are good, and I might need to erase this because we can't see the last one. No, we can. Drawing 1 and 2. So let's look at the last one here. Let's measure it. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's height's 12 units. This is 1, 2, 3. 1, 2, 3. Put 1 here. And this is 1, 2, 3, 4, 5, 6. So what can I do to 4, to the 2 here, and the 1? Well, what can I do to 4 to become 12? I can multiply this fellow by 3, which I get 12. But if I multiply 2 by 3, do I get 6? Yes, so this checks, this checks. And what about this little part of f? If I multiply 1 times 3, will I get this 3? Yes, I will. So this drawing, I think we can call this drawing 7, is a scale copy. Okay. All right. One down. Same type of question. Tyler says figure B is a scale code. This figure right here. This is the original. Original here. And this is the scale copy. It's a scale copy of figure A because all the peaks are half as tall. Do you agree with Tyler? Well, he's saying the peaks, these guys here. Right, this measures 4, this measures 4, this measures 4. Now they measure 2, 2, and 2. What's the problem with this? Well, yes, the height. How did the 4 become a 2? It was times a half, right? So 4 times a half, or 4 divided by 2, which is the same thing as timing a half, got to 2. But guess what? This distance here, right? If it's a scaled copy, this distance should have also been cut by half. So this should actually, the scale copy should have been this wide, right? And likewise, not the height got reduced by half, but these guys here, this line, and I'll put in red, this line should have also been cut in half. And you notice that they're about the same. So did all the dimensions of the original shape get cut in half? No, only the height did, but nothing else did. So remember, if it's a scale copy, all the dimensions, all the sides in the original shape should have been multiplied by half to get to the original. In this case, the only parts that got cut in half were anything that had a height of 4. So no. Alright, and you can talk about what I just said. Triangle O followed by a number of triangles and identify all the scale copies. Okay, so make this a little smaller. Okay, so we want to figure out which one of the scale copies. So this is like the first problem, except it already has it. It comes with numbers. Original. Let's take a look at the ones that are not scale copy. Obviously not scale copy. This is a right angle triangle, so anything that's not a right angle triangle, you can say, see ya, gone, gone. Don't even look at them. Now the rest, you're gonna have to see if they, of all the sides, were multiplied by the same factor. So B is a scale copy, so I'm gonna circle, right? Because the scale copy was times 1, times 1, times 1. And if, remember, if the scale copy is times 1, what happens to the new shape, the new figure? It remains the same. Let's look at C. Well, if you notice from 4 to 5, right, how did the 4 become 5? I have to multiply 4 times a number greater than 1 times a number greater than 1. And I'm just going to leave it at that, greater than 1. And how, so likewise, 3 should have been multiplied by a number greater than 1. But if you notice, 3 now becomes a 2, which is less. So in order to be 2, it was multiplied by a number less than 1. And that already breaks my rule that all the sides here are supposed to be multiplied by the same factor. So knowing that, right, you can always already see that it was multiplied by two different factors here. C is out of contention as well. Let's do this one. This one I think it's pretty obvious. 8, 10, and 6. The scale factor is 2. 4 times 2 is 8. 5 times 10 is 5 times 2 is 10, and 3 times 2 is 6. So this one definitely a scale copy. And then let's look at this. If you think about this, well, I mean, let me change this to what do you call it? Mixed number. 10 over 3 is 3 and 1/3. 8 over 3 is the same thing as 2 and 2/3. Okay, so if you notice here, let's see if this works. 4 multiplied by a factor gives you 2 and 2/3. 5 multiplied by a factor gives you 3 and 1/3. And 3 multiplied by some factor give you 2. Let's see if the same. So let's look at the first one. 3 times, we can set up a little equation here. 3 times something equals 2. Right, let's think about that for a second. Right, so if you want to figure out what that something is, so we can divide by 3 and divide by 3. X, our scale factor, seems to be 2/3. So let's try that out. So let's take this 3 over here and multiply by 2/3. 3 times 2 on the top is 6. At the bottom, well, 3 over 1. 1 times 3 is 3. And we get a 2. 6 over 3. So 3 times the scale factor of 2 over 3 gives you this 2 over here. Let's repeat that was 4. 4 times 2/3. Well, 4 times 2/3, let's put the 4 over 1. 4 times 2 is 8. 1 times 3 is 3. Look, 8 over 3, which is this guy over here. Let's try is 5. 5 times 2/3. Well, put the 5 over 1. 5 times 2 is 10. 1 times 3 is 3. And we get 10 over 3, which we had here. I didn't even actually need to change this to a improper fraction. So were all these 3, the 4, the 5, and 3 multiplied by the same scale factor of 2/3? Yes, they were. So this is a scaled copy. Let's try this one. They're being very tricky over here. So look at 4 and 2. So the scale factor is a half. 4 times 1 over 2. Well, let me actually go this way first. So sometimes when the scale factor is not obvious, we can go this way. How do I go that way? Well, 2 times what is 4? It's times 2. So going bigger, right, is going to be 2, the scale factor. When it's getting bigger, the scale factor is 2. Now, if I know the scale factor going this way is 2, smaller, when it goes this direction, what should it be? The scale factor is going to be the reciprocal of 2, which is 1 over 2. Right? So that's maybe a little trick you can do. So let's apply 4 times a half. 4 times 1 on the top is 4. 4 over 1. 1 times 2 is 2. And what's 4 divided by 2? 2. So this checks out. Let's try it was 5. 5 times a half. Well, numerator times numerator. 5 times 1 is 5. And at the bottom, 1 times 2 is 2. And they left it like this at 5 or half. Tricky, tricky, right? And then 3. Right, let's split it over 1 if you want to make it into a fraction. Multiplied by the scale factor of the half. 3 times 1 is 3. 1 times 2 is 2. 3 over 2, and is that what we have here? Yes. So D is definitely a scale copy. H, well, H, hopefully you can tell that it's not. Look, again, let's go this way because it's probably easier. Right? Think about this, going this way. 2 multiplied by 2 gives me 4. So therefore, this 2 should be also multiplied by 2. But if you notice, this 2 times 2, does it give you 4? No, it gave you 3, right? And then if you look at this number, 2.83 multiplied by 2 is 2.83 times 2, 5? No, it's not. So you can already say that h, not the same scale factor, was applied. Okay, so you can look at it both ways. Okay, so this 2 to become a 4 was times 2, so everything here should have been multiplied by 2, and it doesn't follow that. Not all of them, not all of them, none of them were multiplied by 2 except this first one. So the only scaled copies are B, D, E, and G. All right, so a little start on this one. Figure E, F, G, H, D is a scale copy of A, B, C, D. So if they're telling you scale, it is that it is. So right off the bat, they're telling you it's a scale copy. If it is a scale copy, then they followed, everything was multiplied by the same scale factor, period. So we can notice that there are some sides with not numbers. We can go ahead and fill in. So because it's scale factor, let's look at one that's easy. Let's look at this guy here, the height. That's 3, and this height is 9. So what scale factor did I apply here? Times 3. So everything going that way, in that direction, is times 3, which means going this direction, right? It's going to be times 1/3, the reciprocal. So either way we go, we know what the scale factor is. So 5, so we're going this way, it will be times 3, so this should be 15. This 6, I have the length on top 6, but I don't have the small length here, the corresponding on the small one. So, but going this way, what's 6 times 1/3? It would be 2. So let's fill in all the numbers that we don't know. And we also don't know this guy, the bottom base here. So again, we're going smaller, right? We're going from the E, F, G, H to the A, B, C, D. So we know that it was something times 3 equals 18, or we can do 18 times 1/3, and the original number was 6. There. The first thing you should have maybe worked on was writing all the side lengths of everything. Now we can look at A, B, C, D, E and figure out if any of these are true. So segment GH, so let's look at segment GH. Where's GH? Right here. Highlighted with green. Is 3 times as long as AB. This is AB. No. One is 5. The other one is 9. They're not corresponding sides to begin with, so that shouldn't be compared. So is that even true to begin with? No. Because if it was 3 times as much, if one is 5, the other one should have been 15. So that one, for the love of God, ignore it. The ratio of AB, so look at AB, which is 5, and BC, which is this little guy over here, which is 2. All right, so this is AB, this is BC. The ratio of those two is equivalent to the ratio of EF. EF is here. Put it in green, which is 15, it's corresponding side, and FG, the other corresponding side on top, FG, which is 6. Are those two the same? So let me just write, this is EF, this is EF, and FG. Are these two ratios, 5/2 and 15/6, the same? Well, what's one trick we can do? We can cross multiply them, and you'll notice that 5 times 6 is 30, and 2 times 15 is 30, so the ratios are equal to each other. What's another thing you could have done? Well, 5/2.
Can't be simplified anymore, but can I simplify 15 over 6? Let me just rewrite this again here. 5 over 2, 15 over 6. Well, let me simplify 15 over 6. I can divide the top by 3, and 15 divided by 3 is 5. If I divide the bottom by 3, 6 divided by 3 is 2. Oh, look at that. 15 over 6 is the same thing as 5 over 2. And is 5 over 2 the same as 5 over 2 on the other side? Yeah, so these two ratios are exactly the same. The scale factor of from EFG going from this to this is 1/3. It is true. So just right, because we knew that going from this, from the small one to the big one, everything was multiplied by 3. So therefore, going back from big to small, the scale factor has to be the reciprocal of 3, which was 1/3. The length of segment BC is 2 units. Right here. Is BC 2 units? Yes. So, sorry, C was correct and D was correct. The area of EFG is 3 times the area of ABCD. That's not how it works. Okay, remember, that is not how it works because it's scale factor to the second power times the original area, which is not 3 times. So definitely not true for E. Okay, so here we have 5 rectangles. Q, where's Q? Q, P, R, and they're all scale copies of one another. Great. So the size of the scale factor is from one to another is greater than 1, equal to 1, or less than 1. So let's start with them. From P to Q. So if we went from P to Q, the scale factor is going from P to Q. It has to be greater than 1 because it increased. It got bigger. Right? So the second one, from P to R. P to R. So P going to R, also the scale factor was a number greater than 1. But it got bigger. From Q to S, Q to S, you got, sorry, the scale factor should have been less than 1. Why? Because it got smaller. From Q to R, so from Q to R, what was the scale factor? Greater than 1 because it got bigger. S to P, S and P, so from S to P, it's equal to 1 because they're both the same exact size. They didn't change. R to P, from R to P, so going from R to P, the scale factor was less than 1 because it was a reduction. And finally, from P to S, P to S is equal to 1 because notice that they're exactly the same. Okay. So, let me make this, I know you can't see it on your sheet because it's too tiny. So I'm going to make this a little bit bigger and spend a few minutes here. Now, let's talk about perimeter for a second. Perimeter is a distance around the shape. So if you look at the original perimeter, so the perimeter of this, well, let's put some numbers down first. That's a 4, that's a 2. Let's see on here, this is a 12, and this is a 6. Yeah, so the perimeter of this perimeter, let's try that. The perimeter, let me write small, the small guy here, the small one, and the big guy here. Right, so the perimeter of this small rectangle, well, if we add all the sides, right, the side lengths, 4 plus 2 plus 4 plus 2, we get 12. Right, now we do the perimeter of the bigger rectangle. We get 12 and 12, which is 24. 24 plus another 12 is 36. Well, did I have to do that? Well, if you look at the scale factor here, how did the 4 become 12? How did the 2 become 2? So the scale factor going from this rectangle to this rectangle, all the side lengths were multiplied by 3. So if I knew the perimeter, right, from the small rectangle, all I had to do was multiply it by 3. And I would have gotten 36. Right? So not only when going from the small to large did you multiply all the side lengths by 3, you can also multiply the perimeter of the small rectangle by 3 to get the perimeter of the larger rectangle. Make sense? I hope it does. Okay, so that one is the easy one. So area is where sometimes we get a little stuck. Um, Now, with area, it's not times 3. And going back to one of the previous problems, right? It doesn't work that way. So let's take a look at area of this smaller rectangle. So let me write area. Small area. Let me write large area over here. Large rectangle, that's what I mean. And it's going to be a little bit easier to understand the following problem because it deals with this. So the small area here, it's, well, if you want to find the area, I mean, remember we're talking about the number of square units inside that shape. And if I were to do this, you would say, oh, that's easy. 1, 2, 3, 4, 5, 6, 7, 8. So the smaller area is 8 units squared. Right? What was the scale factor that we used to go from this rectangle to this? Notice that 2 is now 6 and the 4 is 12. So the scale factor, the scale factor was 3. And you're going to say, well, if the scale factor is 3, all we have to do is multiply 8 times 3, and the area of the large rectangle is now 24. Well, that's not really true. Okay, let's see why not. Let's see how I can do this. So 1, 2, 3, 4, 5, 6. And then let me go here. So, sorry, they're not the prettiest of lines. 1, 2, 3, 1, 2, 3, 1, 2, 4, 5, 6, 7, 8. Here we go. Here's 12. Right, so 6 times 12, to find the area, all you have to do is actually literally multiply 6 times 12, and 6 times 12 is 72 units. So using a scale factor of 3, the perimeter was easy. Whatever the perimeter was on the original shape, we multiply by 3, and you got the perimeter of the larger rectangle. But if I multiply 8 times 3, do I get 72? I don't. Okay, but remember the pattern that we found for scale factor, using the scale factor to find the area of the larger rectangle. There's one thing you have to do. It's you have to take the scale factor to the second power and multiply it by the original area. So what was the scale factor? Well, it was times 3. Right, so let me write this. 3 to the second power. What's the original area? 8. 3 to the second power, ladies and gentlemen, is 9. And then times 8 gives you 72. Now, look at that. It works. Right? So, and that was what you had to remember. Let's do these guys. A rectangle, and I left a little box here. It's a rectangle. I don't know dimensions. I don't know what the length and the width, the base, height is. But I know that if I multiply this guy over here times this guy, it's 36 units squared. Right? If I use a scale factor 2, everything's going to double. Right? That's going to double. What's the area now? Well, if you go back to what I said before, we're going to take the scale factor, raise it to the second power, and multiply by the original area. Scale factor. Well, second one, if you double it, take 2 to the second power, and I'm going to put it up here, 2 to the second power. Original area is 36, 2 to the second power is 4, and 4 times 36, 24, carry 2, 144. So this, the area is now 144 units squared. Repeat the process. What if the scale factor was 3? Now this rectangle is 3 times bigger. What's the area inside when the scale factor used was 3? Well, take 3 to the second power. I'm going to multiply by the original area, which is 36. 3 to the second power is 9. And 9 times 36 is a number that I don't know offhand. 324. So 5 to the second power, right? If it's a scale factor, it gets 5 times bigger. And the area is going to be 5 to the second power times 36, or 25, but yeah, 25 times 36, which is going to give us 900. So look how the area is growing. And then a half. Well, just because it's a half, it's still the same fractions. Half to the second power times the original, which is 36. What's half times half? So take half over here and multiply by half. 1 times 1 on the top is 1, and 2 times 2 is 4. So half to the second power is actually 1/4. So take 1/4 times 36. What's 1/4 of 36? It would be 9. Notice. Of course, if you're going to multiply by a scale factor of half, well, the dimensions of that rectangle get smaller, right? So obviously this area also gets smaller. Okay. Oh, and then 2/3. So sorry, we'll do 2/3. So again, 2/3 to the second power times the original area is 36. Take 2/3 times 2/3. So let me do it on the side. 2 times 2 is 4. 3 times 3 is 9. So I get 4 over 9. Then multiply by 36. We can simplify before we multiply, which I have not been doing because I don't know how many of you are okay with that. But I'm going to simplify it by multiply. I'm going to simplify 36 and 9. So 9 goes into 9 one time. 9 goes 36 4 times. And 4 times 4 is 16. There. So the area is 16. Or you can just multiply across. Okay. All right, we're moving. We're halfway done. Let me see if I can get some space here. I can. Oh, magic. So let me get some space. Get some space. A local park is in the shape of a square, so we have a park, and it doesn't kill you to draw a little park in a sheet when you hand out your scrap paper. Okay, and there's a scale here. 1 inch is 200 feet to 200 feet. Right, so local park. Okay, if the park is shown as a square on the map, here's our park. Here's our map. Each side is 9 inches because if it's a square, right? If it's a square, all the sides are the same. So that's 9 inches. This is 9 inches. All the sides 9 inches. How long is each side of the square board? Okay, really? So let's use our scale. 1 inch is to 200 feet. Right? We can set up a proportion. So 9 inches would be how many feet? I don't know. Right, so we cross multiply here. X times 1 is x. 2 times 200 is 1800 feet. So in actuality, right, the park, one of the sides of that park is 1800 feet. All right, if a straight path in the park is 1,500 feet long, how long would the path be represented on the map? Okay, so again, go back to your scale. 1 inch is 200 feet. We know that. So let's put our units, inch, feet. So if 1 inch is 200 feet, how many inches would be 1,540 feet? That's what the question is saying. So our unknown value this time is the inches. Well, x times 200 is 200x. 1 times 1540 is 1540. Divide by 200, divide by 200. X would be how many inches? 1540 divided by 200, 7.7. So on our map, right, the distance of 1,500 feet would be represented by 7.7 inches. Yeah, I know. It's that simple. 8. Kind of hot in here. I don't have the AC on because if I turn the AC on, nobody can hear me. This one I can't scroll down. All right, let's do 8. I need that space on the top. Do it on top. What just happened? Okay, 8. A map of a park has a, so I'll write this down, 1 inch is 1,000 feet. Right, that's the scale. Another map, oops, there's another map. And that one says 1 inch is 500 feet. Which map is larger? Explain or show your reasoning. Okay, so let's think about this. So here's an inch. About an inch. Yeah, that's about an inch. Actually, let me put it the other way. That's 0. And let me use my, now it's a little bit more than that. That's an inch. Inside this inch, I can put 1,000 feet. That's 1,000 feet. And in that same inch, on this side, on the other map, it's 500 feet. Now let's say I had a building, right? Or something that measured, oh, let's say actually 2,000 feet. It might be too tall, actually. Anyways, hypothetically, 2,000 feet. Okay. Well, with the scale on the left, I would need 2 inches, right? Because that's 1,000 feet, and this would be 2,000 feet. Ta-da! There's our building. Done. With the scale on the right, that would be 500, so I need another 500, which would take us to 1,000 feet. I would need another 500, which would take us to 1,500 feet. And guess what? Am I still done? No, I'm not. I would need another, right? That would take us to 2,000 feet. So which of these two scales would give me the larger drawing, in this case, the larger map? Well, it would be this guy here. Okay, and then you guys can figure out. The reason is because on the in the same inch, right? In the same inch, with one scale, I'm saying that's equal to 1,000, and in the other one, the same inch is only equal to 500. So I need more inches here used to show the same distance of 2,000 feet. Whereas here I only take 2 inches to show that. Here I need 4 inches. Okay. You guys can work on that. I don't know what that question is. On the map, the distance between the school and Burger King's. Okay, so I guess I could have used that. So let's say 1 inch is 500 feet. So first of all, inches on top, feet at the bottom. Burger King on the map is 6.5 inches away. What's the distance? The actual distance in feet in real life. So if you were to go take a walk, cross multiply, we get x, and then 500 times 6.5, 3,250 feet. Okay. I am thirsty. 9. What in the world? Scale drawing. You have a scale drawing. A rectangular park is 8 inches by 11. Here's the drawing. Measures 8 by 11. The actual park is 330 yards long. We want the area of the park. Now to find the area of the park, I need this guy here, this measurement. Right? So in order to find that measurement, I need the scale. Do I have a scale right now? Well, I sort of do. I know. You need to use 2 corresponding sides. So we're going to use this side here. This side here measures 11, right? So I know that 11 inches on that map in real life, it equals to 330 yards. That's the scale. Not simplified, but that's the scale, right? So I would never, ever, ever, and let's say I'm just making this up right now, okay, use this 11 inches with this guy here. Because 11 inches does not represent 250 yards, right? They're not corresponding. So you have to make sure you use the corresponding side. Let me paste that before you get funny ideas. Right, so in this case, 11 inches on this map, the drawing, represents 330 yards. Okay, that makes sense. Let's simplify this because I don't like the way that's written. I want to use easier numbers, so I'm going to divide by 11. Right, so I know 11 divided by 11 is 1, and 330 divided by 11 is going to give me 30. So there's my scale. All right, so let me take that. So at the bottom here, that was a real map. There should have been a scale that says, hey, every inch on this map is 30 yards in real life. All right, but they didn't. We had to find it, and we did. Now that I have my scale, put this on the side, I can figure out what this guy is. Right, because I know that on the map is 8 inches. So here's my scale that we just found. So 1 inch is 30 yards. What if I have 8 inches? How many yards would that be? That's what we're trying to find out. Or x yards. Cross multiply, x times 1 is x, and 8 times 30 is 240 yards. So, back here, remove this guy, the question mark is gone, and I can say that in real life, this distance is 240 yards. Now that I have, so now this has 3 steps, right? In order to find the answer to this problem, it's 3 steps. And I'll go back in a second and take back what I just said. But
if you do it this way, now you have the 2 dimensions, and you can say the area. Right? And how do we find the area? Multiply 240, sorry, times 330. So it's, God, we're going to go 240 times 330. And the area of that place there is 79,200 yards squared. That's our final answer. Could we have done this in a different way? And yes, you could have. And I don't know how many of you would have done it this way. So surprise me. Let's go back. Right, so I'll keep my answer here. Right, we found our answer, but could we have done it in a different way? Well, let's take a look at what I wrote before. Remember, if I know the scale factor, can I figure out the area, knowing the original area? So let's find original area. So the original area, this is a little guy here. 8 times 11, which makes this 88. Well, actually, I take that back, because then we have to change yards to inches. No. That wouldn't have worked. No, take that back. Go back. And we're going to live here. That's it. Okay, this is the more accessible way. Okay. Next one. Draw a scale copy of the polygon, right? Using a scale factor of 1/4. Okay. Make life easier for you. And one thing that hopefully you'll do is put some numbers in here, right? You can count the length of the dimension. So this is, I'm going to erase, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is 12. This is 1, 2, 3, 4, 5, 6, 7, 8. This is 1, 2, 3, 4. So this is 2. Sorry, oops. That's 4. This height's 4 as well. 1, 2, 3, 4, 5, 6, 7, 8. That's 8 as well. And this is 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes. Just make it prettier. Erase these things. So we have the dimensions. All right, so before you even start drawing. So scale factor is 1/4. What do we know that's going to happen to our polygon? It's going to go smaller because we're going to multiply by a number less than 1. So smaller it shall be. Okay, so everything is going to be small. So if you want to take your calculator, multiply 12 times 1/4, you can multiply 8 times 1/4, and you have to multiply 4 times 1/4. So you got to do it. There's three numbers. All right, so 1/4 of 12 is 3, 1/4 of 8 is 2, and 1/4 of 4 obviously is 1. So that's how much smaller it's going to be. Okay, so let's get the 8. The 8 here is now 2. So it's going to be 1, 2 right there. The 12 is going to be 3. 1, 2, 3 right here. This is another 12. So this is 12 multiplied by 1/4 is 3 again. And then we're going to go up. And the 8, that was this height here. This height 8 is no longer 8, it's now 2. So we go up 2. Right? And then we're going to make a left turn. What 1/4 of 4 is 1. So we're going to go left 1 and up 1. Then we go right 1 and 1. And there's 2 ones. This is a scaled copy of the polygon using a factor of 1/4. We knew it was going to be smaller. We multiply all the side lengths by 1/4, and we got our new dimensions. That's it. Use the map distances. Find the actual distance. The map uses a scale of 2 centimeters. So here is our scale. You don't have to, okay? But you want to change it to a unit rate, right? So instead of 2 to 21, you want to change it to 1 centimeter. You don't have to. You can. I don't see why you shouldn't. So 2, let's change it to 1, divide by 2, so which means I divide this by 2. It is now, so that means that every 1 centimeter is 10.5 kilometers. That doesn't bother you. If this doesn't bother you, I should say 2 centimeter 21. You can keep it as that. Remember, if the question was one of those questions where you had to compare scales to see which one would result in a largest drawing or the smallest drawing, then I would definitely change it. But in this case here, it's just a simple proportion problem. Your choice. So I'm going to use this. So instead of using 2 centimeters 21, I'm going to use the simplified rate, the unit rate version. So what's 8 centimeters? What does 8 centimeters represent? It would be how many kilometers? That's what the question is. So 1 centimeter is 10.5 kilometers. If I have 8 centimeters, how many kilometers would that be? And that's what the question is saying, right? Cross multiply, we get x times 1 is x, and then 8 times 10.5 is 84 kilometers. And repeat the process again. So this problem is kind of boring. 8 centimeters, x kilometers. No, sorry, 9 centimeters. And this time around, we want to know what 9 centimeters would be in real life. X kilometers, and then 9 times 10.5 is 94.5 kilometers. And just because we can, for the last one, I'll actually use the original scale. 2 centimeters is 21 kilometers. What's 20 centimeters? What would 20 centimeters be in real life? So x kilometers, cross multiply, 2 times x is 2x. 21 times 20 is, is 420. Divide by 2, divide by 2, x equals 210. So if you use the scale that was not a unit scale, then you had an extra step here, right? To isolate your variable, you have to divide by the coefficient, because the coefficient wasn't 1, so you have to divide it by 2, and just create an extra step. Not a big deal. Okay. 12. A picture uses scale 3. Okay, so 3 inches is worth 45 feet in real life. Again, you may use this as it is. You want to switch it to 1 inch. As long as it doesn't give you a repeating decimal, for example, then I would say it's probably a good idea. It makes life easier. So divide by 3, and then 45 divided by 3 is 15 feet. So this works out. Right, so if you divide it and you look at your calculator, and I'm making this up, and you got a number, and your calculator is saying 16.33333. Now what? Well, in this case, you're probably better off not doing this and leaving it in whatever scale it was previously. Okay, because if you're definitely not going to use this 16.33 repeating, so it might force you to use 16 1/3. But if it was 6666, it was 16 2/3, etc. So you're better off not doing that. So in this case, it worked out nice. 45 divided by 3 is a nice whole number, 15. So you can now come and use the proportion. So instead of using 3 inches to 45 feet, use 1 inch to 50. It just makes life easier. So
1 inch is 15 feet. If I have 90 feet, how many inches would that be on my drawing? That's what the question is asking, right? Cross multiply, we got 15 feet, 15x, sorry, equals 90. Divide by 15, divide by 15, x equals 6. So 90 feet would be equivalent to 16 inches in my drawing. 300 feet. 1 inch is 15 feet. X inches, because that's what I'm trying to find. And we have 300 feet in real life. How do I draw that? Right. Well, cross multiply, we have 15x. 1 times 300 is 300. Divide by 15, divide by 15. X equals 20 inches. Okay. Last one I'm going to do with the original. I'm not going to use the easy one. I'm going to, the simplified one, I'm going to use the original scale that they gave us. So let me use this original. So just to see. 3 inches is 45 feet. And then we want to know inches. I don't know how many inches. And then we have 67.5 feet. How many inches would that be? All right, so now I have to multiply. I get 45x. Already my numbers are big, right? It's not 1 in 15 anymore. Keep dropping the phone. 3 times 67.5, 202.5. So this is 202.5. Divide by 45. Divide by 45. The numbers are definitely bigger, right? So 202.5 divided by 45 equals 4.5. So that, in our drawing, would be 4.5 inches. Not a big deal when you have a calculator. I understand that. So it's a matter of choice. It's like saying, it's like walking around saying, hey, I ate half of a pizza, right? 2/4 or whatever not, 4/8. It's much easier dealing with this, right? The simplified version. It just makes life. It's not mandatory at all. So nobody can tell you that you have to simplify. You know, it's just a matter of working is easier. That's all it is. A matter of choice, actually. Okay, but it does make life easier. Your task for Thursday for the bonus 2 points, if you're interested, is to have, I'm not even going to write this down, is to wear mix matched socks. 2 socks that are not the same. So the left side is pink, the right side is checkers, so they can't be the same. And that gets you 2 bonus points. All right. Not a fan of this picture, of this question, because I think it's a little bit tough to see. So let's try this. On the map is a scale of 1 inch, 12 feet. So every inch on my map in real life represents. So if that's 1 inch, in real life, that's saying that's 12 feet. Okay, so let's get that. Now, there's a restaurant, right? And the area of the restaurant is 16 inches square. And I don't know what the shape of the restaurant is. Okay, I don't know. This is the restaurant. And in the restaurant, 60 inches square. What does that mean? Well, it means that inside the restaurant, right, in my map, in my drawing, so I'm talking about in my drawing, right, this is about 1 inch, right? I should have made the restaurant a little bigger. So anyways, in my drawing, imagine, this is a 1 inch by 1 inch square. If I told you to find the area of that for me, right? The area, that area would be 1 inch square, right? Because it's 1 times 1. The restaurant in my drawing is made up of 60 of these. So if I take this and multiply by 60, right? 60 of these. side by side. I don't know what configuration, but side by side, if I took 60 of those, I would get, the layout of the restaurant. It might be a rectangle, it might be a square, it might not be, but I need 60 of these. All right, so if in my drawing, that would be the size of the restaurant. Okay, so hopefully that makes sense. So that's what 60 inches squared means. Right, so if I got 60 of these, right, this is every single one of these is 1 inch squared, 1 inch squared, 1 inch squared. If I got 60 of these and put them together, right, whatever shape, that represents the restaurant. Okay, so let me take these out. Right, so here's my restaurant, and in this restaurant, there is 60 of these 1 inch squares. That's what, first of all, okay, that's what the first sentence says. Han says that the actual area of the restaurant is 750 square. I don't know how he got that. Because he multiplies 60 by 12. Well, it doesn't really make sense. So, if in real life, right, so because we have the scale, in real life, this, remember I told you about, depending on the glass that you have, about that tile? This measures, not tile, big tile. This measures 12 feet, 12 feet. So in real life, right, every inch squared in real life actually represents this square. A square that measures 12 feet and 12 feet. And how did I get the number? Because it says here, the scale, right, that if this side was 1 inch, in real life it's 12 feet. If this side is 1 inch, in real life it's 12 feet. Are you okay with that? Right, so I'm just showing you what this guy here is in real life. So in real life, this 1 inch squared is represented by this 12 by 12 square. And what's the area of this? 144 inches. Sorry, inches, not inches. Feet square. 144 feet square. Okay? So, if I represented one of these with these, right? But how many of these are there? There are 60 of them. So if I were to go out there in real life and I got 60 of these squares, right? And every square measures 12 going this way, 12 here. That's one. So now I got to take another one. So this measures 12 feet, and this measures 12 feet. Right? And then put it right next to it. And then I'm going to take another one. 12 feet. This measures 12 feet. And this measures 12 feet. Right? And it's 144 feet squared inside. 144 feet squared inside. So how many of these are happening together? Well, it's 60 of them. So I have, the restaurant is made up of 12 squares in real life that measure 12 feet by 12 feet. Okay? So the area, the total area, well, one of these is 144 feet square, right? Or square feet. But how many of them do we have? We multiply that times 60. If we multiply that by 60, 144 times 60, the area of that restaurant, oh, geez, 8,640 feet square. It's not a restaurant, it's like a mansion. It's huge. Well, I take that back. Not huge. It's a very good sized restaurant. Okay. But that's what you have to understand here. Hopefully that makes some sense. 14 had a mistake, which was corrected. Hopefully you corrected it. This was a 1, so some of you got a sheet where this was a 1, right? And this was a 1. Please make a correction, and the correction is 2 centimeters, 2 centimeters. Here's a scale drawing of a swimming pool where 1, so here's a scale, 1 centimeter represents 12 meters. Right, so I drew my fake swimming pool in my notebook, the one I wish I had right now, and I used this scale. Okay, how long and how wide is the actual swimming pool? Well, okay, let's try it out. Let me write the scale again over 1 centimeter is 12 meters. So let's do this guy here. What is 6 centimeters? How wide? What's the length of my pool? Now, if I use my scale, right, 1 centimeter to 12 meters, and I have 6 centimeters in my notebook, the drawing of my swimming pool that I don't have. How many meters is that? Well, if I cross multiply, I get x and 72 meters. All right, it's a decent size, right? So in real life, that pool, that's 6 centimeters, it represents 72 meters. Not bad. And then what about the 2.4 over here? Well, again, let's use the scale. 1 centimeter is 12 meters. This time around, I want to know what 2.4 centimeters looks like in real life. So x meters, because that's what I'm trying to find. X times 1 is x, and 12 times 2.4, I have no idea. 12, 2.4. What the heck? 12 times 2.4, 28.8 meters. Jeez. That's a big pool. Big pool. That's a big pool. That's 28.8 meters. So that's my pool. How long and how wide? Okay. Now that we know this, so imagine this is my pool, and I decide to draw it in my notebook. And I decide to use this scale. So, right, 1 centimeter to 12 centimeters, and this is what I got in my notebook. Right? So in my notebook, I drew my swimming pool, and measure 6 centimeters going this way, and 2.4 centimeters going this way. Right? Now, my brother comes along and says, "Nah, I don't like your drawing. I want to use a scale 2 centimeters to 12 meters. And he's going to draw the swimming pool we don't have in his notebook. Is his drawing of the swimming pool going to be longer, right? Bigger? Is the drawing going to be bigger or smaller than the one I already drew? Well, you got to look at his scale, which is this one. You got to look at my scale, which is this one. Remember the apples that we talked about in class? Can I compare? Can you tell me which one is the better deal? Well, not yet. So what do I have to do to this guy here? Well, I'm going to simplify. So instead of looking at it as 2 centimeters or 12 meters, let me change that. So let me divide that by 2, and the bottom by 2, right? 2 divided by 2 gives me 1 centimeter. Oh, and 12 divided by 2 gives me 6 centimeters. Now I can answer the question. Look, this is 1 centimeter to 6 centimeters. The scale that I used was 1 centimeter to 12 centimeters. So if my drawing came out, this 6 centimeter, 2.4 centimeter are the dimensions of my drawing. If my brother comes and draws that same swimming pool, but using this scale, is his drawing going to be bigger or smaller? Obviously, what do we talk about? Because here, every centimeter represents less distance, right? His drawing is going to be bigger, right? It has that opposite effect, right? It takes more centimeters for him to represent the same distance. Let's take a look at how would that work. So over here in this, I'm going to take this, right? Over here, I don't need all this. So let's take a look at his drawing, which I'll do over here. So his scale, 1 centimeter to 6 meters. Okay. I need to pull back. And here's our pool. So let's use his scale. 1 centimeter, 6 meters. So if I have 72 meters, or he has 72 meters, how many centimeters will he need? Well, cross multiply, we get 6x equals 72, divided by 6, divided by 6, x equals 12. So you can already see that this part over here, this line, the length here, for him is going to be 12 centimeters. Right? Well, let's look at the width of the pool using his scale. Let me do it over here in the corner. 1 centimeter is 6 meters. And this time around, we want, x centimeters, and how much is the length in real life for a pool? 28.8. Let's cross multiply this. So we get 6x equals 28.8 divided by 6 divided by 6. X equals 28.8 divided by 6 equals 4.8. So in his drawing, my brother's drawing, this side over here, up and down, is represented by 4.8 centimeters. So look at his scale, 1 centimeter to 6 centimeters. My scale was 1 centimeter to 12 meters, right? That was my scale, original one. So notice that for him, the centimeters represented less distance in real life than mine. Therefore, his drawing ends up being a little bit longer, okay, larger. Okay, that's that. You know what to do.